What if I told you China is building projects so insane? They sound like science fiction. Bridges floating in the sky, trains faster than planes, underwater tunnels no one thought possible. In this video, you'll discover 6 mega projects that are breaking every rule in engineering, logistics, and speed. Back to back, no fluff, just mind-blowing innovation. Let's dive in. This is China's race to build the impossible. You're standing at the edge of a massive gorge. The wind whips across your face. Your eyes strain to see the bottom of the canyon below, but it disappears into mist and shadows. A single step forward would mean certain death. Then you look up and see it. A ribbon of concrete and steel suspended in the sky. The Huajiang Canyon Bridge. Let's put this bridge's height into perspective. At 2,051 feet above the canyon floor, the Huajiang Bridge stands taller than 3 Washington monuments stacked on top of each other. If you dropped a bowling ball from the deck, it would take nearly 11 seconds to hit the ground. That's enough time to read this entire sentence twice. But this comparison only scratches the surface of what makes this bridge a true engineering wonder. The bridge's location itself tells a fascinating story. Situated in China's Guizhou province, it spans one of the deepest canyons in Asia. The region's terrain is so challenging that for centuries, entire communities remained isolated from each other, separated by these natural barriers. Local legends tell of villages that could see each other across the canyon, but required a full day's journey to actually meet. The project began in 2013, with many experts claiming it couldn't be done. The first challenge was simply surveying the site. Teams had to rappel down the canyon walls to take measurements and soil samples. Several geologists refused the job, calling the cliff faces too unstable. But a determined team pushed forward, spending 3 months mapping every inch of the canyon. But height isn't the only thing that makes this bridge extraordinary. The construction story behind it reads like an engineering thriller. The team faced 3 major challenges that nearly made this project impossible. First, the wind. At this height, gusts can reach speeds of over 100 miles per hour. Engineers had to design a deck that could handle these forces while staying stable enough for vehicles to cross. They developed a ground-breaking aerodynamic design that lets the wind pass through special vents, reducing pressure by 40% compared to traditional bridge designs. The testing phase alone took 6 months, with engineers using advanced wind tunnels to simulate every possible weather scenario. In one dramatic test, a scale model was subjected to hurricane-force winds for 72 continuous hours. Previous designs failed within the first day, with miniature sections buckling or twisting. The final design stood firm, swaying less than half an inch at the center span, a movement practically imperceptible to drivers crossing the actual bridge. The second challenge? The canyon itself. The steep walls made traditional construction methods useless. Workers couldn't simply build scaffolding from the ground up. The canyon was too deep and unstable. Instead, they had to construct the bridge from both sides simultaneously, using a method called cable-stayed cantilever construction. Think of it like building a massive diving board from both cliffs at once, hoping they'll meet perfectly in the middle. This construction method required unprecedented precision. Each section had to be perfectly balanced as it extended out over the void. Special GPS systems were installed to track movement down to the millimeter. The slightest miscalculation could send thousands of tons of steel and concrete plummeting into the canyon below. On the day the 2 sides were scheduled to meet, engineers held their breath. The gap between the sections had to be within 3 centimeters to make the connection. Temperature changes overnight could expand or contract the steel, throwing off calculations. The team chose to make the final connection at dawn, when temperatures were most stable. When the sections aligned with only 2.2 centimeters difference, the construction crew erupted in celebration. But the most daunting challenge came from an unexpected source: temperature. The extreme height difference between the canyon floor and the bridge deck creates temperature variations of up to 30 degrees Celsius. This means different parts of the bridge expand and contract at different rates. The solution? A revolutionary expansion joint system that can move up to 2 meters in any direction, acting like a giant accordion to keep the bridge stable. These joints represent a breakthrough in bridge engineering. They contain special sensors that continuously monitor temperature pressure, and movement. The data is fed into a central computer system that predicts when and how the bridge needs to adjust. It's like giving the bridge its own nervous system. The construction process pushed human ingenuity to its limits. Workers had to operate cranes at heights where oxygen levels are noticeably lower. Every steel cable and concrete pour had to be precisely calculated. A mistake of even a few millimeters could spell disaster when building at this scale. The construction team even developed new safety protocols that are now being adopted as standard practice for high-altitude construction worldwide. The human stories behind this bridge are just as impressive as the engineering. Over 400 workers lived in temporary housing on the canyon rim for 3 years. Many were local villagers who had never worked on construction projects before. They received specialized training and now form an elite workforce deployed on other mega projects across China. One worker, Li Wei, started as a basic laborer and is now a sought-after specialist in high-altitude cable installation. The numbers behind this project are staggering. The main span stretches 1,140 feet across the canyon. The bridge deck contains enough steel to build 3 Eiffel Towers. The foundation pillars go so deep into the canyon walls that they could support a structure twice as heavy. Each main cable can withstand the weight of 360 fully loaded trucks. The concrete used isn't ordinary either. Engineers developed a special high-strength mixture that can withstand extreme temperature changes and resist cracking under enormous pressure. This new formula is now being studied by construction companies around the world for use in other mega projects. To test the durability of this concrete, researchers subjected sample blocks to pressures equivalent to being at the bottom of the ocean, then rapidly heated them to temperatures found in a blast furnace. Standard concrete would shatter under such conditions. The Huajiang mixture showed only microscopic stress fractures. But here's what makes this bridge truly revolutionary. It's not just about crossing a canyon. The Huajiang Bridge is part of a larger network that's transforming China's rural regions. Before this bridge, the journey around the canyon took over 4 hours. Now, just 7 minutes. Think about that change. A farmer can now reach markets in a fraction of the time. Students can access better schools. Emergency services can reach remote villages that were once almost inaccessible. This isn't just a bridge. It's a lifeline that's reshaping an entire region. The economic impact has been immediate and dramatic. Villages that were once considered too remote for tourism are now popular destinations. Local businesses report revenue increases of over 200% since the bridge opened. Property values in the surrounding areas have tripled. The bridge has literally put this region on the map. One local entrepreneur, Ms. Jiang, converted her family home into a guest house. Before the bridge, she might see 2 or 3 visitors a month. Now she hosts over 100 guests weekly, many international tourists, coming specifically to see the bridge. Her story has been repeated across dozens of villages in the region. The technology developed for this project is already influencing bridge design worldwide. Engineers from over 30 countries have visited the site to study its innovations. The special wind-resistant deck design is being adapted for bridges in other high-wind regions. The temperature compensation system is becoming a new standard for extreme environment construction. But perhaps the most fascinating aspect is what this bridge represents for the future of engineering. We're entering an era where the impossible is becoming possible. The solutions developed for the Huajiang Bridge are paving the way for even more ambitious projects. Engineers are already talking about bridges that could span even greater heights and distances. The success of this project has opened up new possibilities. If we can build a bridge this high, what other engineering challenges can we overcome? Could we build bridges across ocean trenches? Span entire mountain ranges? The Huajiang Bridge isn't just a record holder, it's a preview of what's coming next in the world of megastructures. Right now, somewhere in the world, engineers are looking at the Huajiang Bridge's success and asking themselves, what if we went even higher? Plans are already being drawn up for a bridge that could shatter this record. But the location and design of this potential new champion are being kept strictly under wraps. The only question is, how much higher can we go? Imagine boring through solid rock beneath one of the world's mightiest rivers, creating a tunnel so massive you could fit a 5-story building inside it. Right now, beneath China's Yellow River, thousands of workers are creating the world's largest underwater tunnel using machines with the power of 26 million pound-feet of torque. While the world debates China's economic troubles, the communist regime is silently betting billions on a project that's shattering records for both size and speed. The Jinan Huanggang tunnel is rewriting the rules of what humans can build, and the pace at which they're building it raises serious questions about the true cost of China's infrastructure miracle. China has always built big. The Great Wall, Three Gorges Dam, and the world's largest high-speed rail network all show China's obsession with infrastructure on an almost unimaginable scale. But those projects were built above ground, where construction challenges, while enormous, were at least visible and relatively understood. The Jinan Huanggang tunnel takes Chinese ambition to an entirely new level, or more accurately, a new depth. This isn't just another road. This is a 3.6-mile engineering marvel being carved beneath the Yellow River, connecting the eastern city of Jinan with new development zones in Shandong province. For context, while not the longest underwater tunnel in the world, Japan's Seikan Tunnel stretches 33.5 miles, and the Channel Tunnel, connecting England and France, runs 31.4 miles. The Jinan Huanggang Tunnel sets records in an entirely different dimension: size. The tunnel's diameter is a massive 55.8 feet, more than twice the size of the Channel Tunnel's 25-foot diameter tubes. So why is China attempting something so ambitious? The answer lies in both economics and strategic development. The Yellow River has long been both the cradle of Chinese civilization and a natural barrier to transportation. As China's second longest river, it divides important regions and creates bottlenecks for commerce and transportation. The current route between areas north and south of the river requires vehicles to take significant detours or use congested bridges. This tunnel aims to cut travel time dramatically and open up new development opportunities. The Jinan Huanggang Tunnel will feature 6 lanes of traffic in a revolutionary double-decker configuration, with northbound traffic on the upper deck and southbound on the lower deck. The design speed is 60 kilometers per hour, making it a crucial north-south passage that enhances connectivity between Jinan's main urban area and what Chinese authorities describe as the starting area for the transformation of new and old kinetic energy. This project is especially significant for Jinan, a city of 9.4 million people and the capital of Shandong province. The tunnel connects the established urban core south of the Yellow River with a new state-level strategic pilot zone for free trade, innovation, and reform on the north side. Chinese planners view this connection as critical for economic integration and future growth in the region. Construction began in July 2022, with a groundbreaking ceremony held on the north bank of the Yellow River. The underwater boring portion started in September 2024. What's remarkable isn't just the size, but the speed. The China Railway 14th Bureau Group completed the underwater section in just 110 days, setting world records for both size and construction pace. The total project spans approximately 5.8 kilometers, 3.6 miles, with the tunnel section about 4.8 kilometers, 3 miles long. The mechanized tunneling section using the Shield boring machine is approximately 3.3 kilometers, 2 miles long. This makes it substantially shorter than famous underwater tunnels like the Channel Tunnel, but its diameter and construction speed are what make it extraordinary. To understand the true scale of this project, we need to look at the numbers. The main tunnels have an internal diameter of 15.4 meters, 50.5 feet, and an external diameter of 16.8 meters, 55.1 feet, wide enough for 3 lanes of traffic on each level. The geology presents major challenges. The tunnel must cut through clay, silty clay, sand, calcareous nodules, and glued sand, all while managing significant groundwater pressure. The boring machine itself is an engineering marvel called Shanhe. Manufactured by Herrenknecht, this mixed-shield tunnel boring machine, TBM, has an excavation diameter of 57.4 feet, 17.5 meters, roughly 5 stories tall. The cutterhead has 7,510 horsepower and about 26 million pound-feet of torque. The cost of this single machine is estimated at $80 million. This makes Shanhe one of the largest tunnel boring machines ever deployed, comparable to Big Bertha, used for Seattle's Highway 99 tunnel, and Martina, used in Madrid's M30 highway project. The key difference is that Shanhe must operate beneath a major river with significant water pressure. What makes the Shanhe TBM special is its ability to operate under extreme pressure. It's built to withstand up to 7.5 bar of pressure, 7.5 times normal atmospheric pressure at sea level, and Its excavation chamber can handle up to 15 bar using a specialized automatic air cushion to balance pressure, maintain stability, and prevent collapse or flooding. The tunnel boring process for a project of this scale is fascinating. The cutting wheel is equipped with a flushing system to help prevent clogging from the clayey soil. A telescopic camera system in the excavation chamber monitors the cutting bits and tunnel face, reducing the need for dangerous hyperbaric intervention by maintenance workers. The machine advanced at a record-breaking pace of 52.5 to 59 feet, 16 to 18 meters per day, achieving a monthly progress of about 1,400 feet. This pace would have been considered impossible just a decade ago, but it raises important questions about the trade-offs between speed and safety. The human dimension of this project shouldn't be overlooked. Thousands of workers are involved in this massive undertaking, working in shifts around the clock to maintain the ambitious schedule. Tunnel construction remains one of the most dangerous forms of infrastructure development, combining risks from heavy machinery, confined spaces, and unpredictable geological conditions. In China's drive for rapid development, worker safety concerns have often been secondary to project timelines. While specific safety records for this project aren't publicly available, China's construction industry is known for higher accident rates than Western counterparts. Tunnel projects worldwide are among the most dangerous construction environments, with risks including cave-ins, flooding, toxic gas exposure, and machinery accidents. The engineering challenges extend beyond just boring the tunnel. The shield segments, the interlocking concrete rings that form the tunnel walls, must be precisely manufactured and installed. For the Jinan Huanggang tunnel, approximately 500 pipe rings of underwater shielding were installed during the 110-day underwater boring phase. Each of these massive concrete segments must be designed to withstand not just the pressure of the water and earth above, but also potential seismic activity. The Yellow River Basin has experienced earthquakes throughout its history, and any tunnel design must account for ground movement that could damage or breach the structure. The environmental challenges are also significant. The Yellow River is ecologically sensitive and prone to flooding and sedimentation, earning it the nickname China's Sorrow for its historic tendency to flood and change course. Any major construction project affecting the river requires careful management of both immediate impacts and long-term stability. Engineers developed innovative waste slurry treatment methods, including jaw crushers, dual-line pipeline hydraulic quarrying devices, and waste slurry concentration systems to ensure environmentally friendly tunneling. This aspect of the project highlights China's growing awareness of the need to balance rapid development with environmental protection, though critics would argue that environmental concerns remain secondary to project completion. The Jinan Huanggang Tunnel project is being constructed by the China Railway 14th Bureau Group Company Limited, one of China's premier infrastructure development companies, with investment from the Jinan Urban Construction Group. This public-private partnership model is common for major infrastructure projects in China, combining government backing with corporate efficiency. Despite the challenges, the Chinese government has continued to push the project forward with remarkable speed. This raises an important question. Is this tunnel worth the enormous financial and human cost? From an economic perspective, Chinese authorities clearly believe the investment will pay off through improved transportation efficiency and regional development. The tunnel connects Jinan's urban core with strategic development zones, potentially catalyzing economic growth across the region. The project also fits within China's broader strategy of using infrastructure investment to maintain economic growth as traditional drivers, like export manufacturing and real estate development, slow down. Infrastructure spending has become increasingly important for maintaining employment and GDP growth targets, especially in the aftermath of economic disruptions from the COVID-19 pandemic. The Jinan Huanggang Tunnel showcases China's growing expertise in infrastructure megaprojects. The technology and techniques developed for this tunnel have applications far beyond China's borders. Chinese construction firms are actively marketing their tunneling expertise internationally, particularly to countries participating in the Belt and Road Initiative. This represents a sophisticated form of economic diplomacy, exporting not just products, but entire infrastructure development systems. As Chinese firms gain experience with projects like the Jinan Huanggang Tunnel, they become more competitive for international contracts, extending China's global influence through infrastructure partnerships. The tunnel project showcases several technological innovations. the massive diameter required specialized engineering solutions not used in previous tunnel projects. The composite lining materials must balance strength with flexibility, particularly in an area that could experience seismic activity. Air quality management represents another major engineering challenge. A tunnel of this size requires massive ventilation systems to remove vehicle emissions and maintain oxygen levels. Complex fire suppression and emergency evacuation systems are being integrated to ensure safety once the tunnel is operational. When completed, the tunnel will incorporate state-of-the-art traffic management systems, including sensors to monitor vehicle flow and environmental conditions, automated incident detection, and dynamic message signs to communicate with drivers. Modern tunnels are as much about information technology as they are about concrete and steel. The total cost of the Jinan Huanggang tunnel project hasn't been publicly disclosed, but based on comparable projects, experts estimate it at several $billion. For comparison, the much longer but narrower channel tunnel cost approximately $21 billion in today's dollars. Maintenance costs will be substantial once the tunnel is operational. Underground infrastructure, especially beneath rivers, requires constant monitoring and periodic renovation to address water infiltration, structural fatigue, and systems degradation. The anticipated service life of modern tunnels is typically 100+ years, but this assumes regular maintenance and periodic major renovations. The project is scheduled for completion in late 2025, though infrastructure projects of this scale often face delays. Once operational, it will dramatically transform transportation in Jinan and set new benchmarks for infrastructure projects worldwide. The Jinan Huanggang Tunnel represents more than just a transportation link. It's a statement about China's engineering capabilities and determination to overcome natural barriers through human ingenuity. While questions remain about the economic rationality and safety of such rapid construction, there's no denying the technical achievement it represents. As cities worldwide grapple with transportation challenges and natural barriers, projects like this offer valuable lessons about the possibilities and limitations of modern infrastructure development. The techniques developed for the Jinan Huanggang Tunnel could influence underground construction for decades to come, potentially making previously impossible infrastructure connections feasible. As the Jinan Huanggang Tunnel inches toward completion, engineers have encountered unexpectedly high pressure zones that are testing the limits of even the mighty Shanhei machine. The race to finish by late 2025 raises a critical question. Is China prioritizing propaganda deadlines over engineering prudence? What's happening beneath the Yellow River might be the ultimate test of whether breaking speed records and breaking safety standards go hand in hand. And the answer could permanently change how we view China's infrastructure miracle. What if ships could sail over mountains? China didn't ask, what if? They built it. Gupitan Shiplift, a $7.7 billion mega elevator that hauls 10,000-ton ships, each as tall as a 66-story skyscraper, a jaw-dropping 199 meters into the sky, like a floating titan defying gravity itself. But why build this monster in the first place? The answer reveals a masterclass in strategic thinking that goes far beyond simply moving cargo from point A to point B. China's inland trade faces a brutal challenge: mountains, cliffs, and unpredictable terrain. Nowhere is this more obvious than the Huajiang River in Guizhou province, a region where traditional transport methods are slow, expensive, and often dangerous. The geography here isn't just challenging, it's hostile. Sharp limestone peaks erupt from the landscape like dragon's teeth. Narrow valleys plunge hundreds of meters below. Monsoon seasons transform gentle streams into raging torrents. For centuries, this region was known as the mountain that devours men, due to its treacherous passages and deadly landslides. Before the ship lift, moving cargo through this labyrinth of rock and water was nearly impossible. Ships had no path forward. Trucks crawled along crumbling roads, barely holding their ground against landslides. Traditional canal locks, which have worked in other parts of the world, were too slow and impractical for this extreme landscape. A conventional lock system would have required an endless chain of at least 20 separate chambers to navigate the nearly 200-meter elevation change. The economic cost was devastating. Shipping a single container from Guizhou to Shanghai could take up to 2 weeks and cost 3 times more than comparable distances elsewhere in China. Local industries suffered. Foreign investment avoided the region entirely. An entire province with 36 million people larger than most European countries, remained economically isolated in one of the world's fastest-growing economies. So China did something radical. Instead of forcing the river to adapt to trade, they made trade adapt to the river. That's where the Gupitan ship lift comes in. A machine so powerful it compresses 4 days of travel into just 2.5 hours. Imagine a ship the size of a football field entering a colossal steel chamber. The gates slam shut, sealing it inside with precision-engineered hydraulic doors weighing 400 tons each. Then, the magic begins. Massive pumps roar to life, flooding the chamber with water, cradling the vessel in a liquid elevator. The chamber itself weighs 3,000 tons empty, but with water and a fully loaded cargo ship, this weight balloons to over 11,000 tons. Slowly, the entire structure rises, straight up, as if the river itself is lifting it over the mountain. The ship ascends, climbing higher than the Statue of Liberty and the Great Pyramid of Giza combined. From inside the ship, the experience is surreal. The ground falls away, the world outside shrinking like a disappearing valley. Through small portholes in the chamber walls, passengers can glimpse the shrinking landscape below. River becomes ribbon. Villages become specks. The vast scale of the surrounding mountains becomes apparent only when you're halfway up their imposing faces. When the chamber reaches the upper reservoir, the forward gates open to reveal a new world, a sprawling lake where just minutes before there was nothing but air. The ship glides forward, continuing its journey as if it hadn't just performed an engineering miracle. It's not just a shortcut, it's a game changer, a river highway carved into the sky. At the heart of this machine is a floating fortress, a colossal ship chamber, 40 meters long and 12 meters wide, holding 500 tons of steel and water. But how do you lift something this massive without disaster? The answer lies in raw mechanical power and surgical precision. The chamber moves along 4 massive concrete towers that function as both guide rails and structural support. These towers are anchored deep into the bedrock, with foundations extending 70 meters below the visible structure. Each tower contains redundant systems of cables, counterweights, and emergency brakes. 256 steel cables, each strong enough to tow a jumbo jet, guide the chamber along a gear rack climbing system. These aren't ordinary cables. Each is composed of 127 individual strands of high tensile steel, twisted together in a precise pattern that maximizes strength while minimizing weight. If laid end to end, the cables would stretch over 80 kilometers. Interlocking metal teeth lift the entire structure vertically, like a skyscraper-sized cogwheel. These teeth must engage perfectly on every cycle, with tolerances measured in millimeters despite the enormous forces involved. The teeth are made from a special alloy that's both incredibly hard yet flexible enough to absorb micro vibrations that would otherwise damage the system. A nut column safety system absorbs the violent shockwaves from winds, waves, and even earthquakes. The lift must stay perfectly balanced, even under the tremendous weight of ships and turbulent water pressure. Sensors throughout the structure constantly monitor for the slightest imbalance, automatically adjusting the lifting mechanism to compensate. Counterweights and hydraulic dampers help stabilize the motion, ensuring that even with millimeter-level precision, the system doesn't buckle under pressure. The dampers themselves contain enough hydraulic fluid to fill an Olympic swimming pool and can absorb forces equivalent to a small meteorite impact. The power requirements are staggering. The lift consumes enough electricity to power a small city, though much of this is generated by the dam's own hydroelectric turbines. Backup generators can provide emergency power sufficient to safely lower the chamber in case of a grid failure. Every cycle is a high-stakes ballet of physics and engineering. One miscalculation, and the entire 10,000-ton mass could slam into the structure with catastrophic force. The control systems feature quintuple redundancy. 5 separate computers continuously check each other's calculations, with any disagreement triggering an immediate safety protocol. Each lifting cycle takes just 30 minutes. In 2.5 hours, an entire mountain range is bypassed. The system can complete up to 24 full cycles per day, moving nearly 5 million tons of cargo annually. A massive shortcut, a game changer for China's trade routes. But efficiency wasn't the only goal. This project had a far bigger agenda. At first glance, the Gupitan ship lift seems like a futuristic way to move cargo. But beneath the surface, it reveals a much deeper strategy, one that rewrites the economic map of China. For decades, Guizhou province was a logistical dead zone. its economy was trapped by the same mountains that made transport nearly impossible. Industries struggled, trade crawled, entire regions were cut off from prosperity. The province consistently ranked among China's poorest, with per capita GDP less than a third of coastal regions. Now, that's changed. With this vertical water highway, Guizhou is directly linked to China's economic backbone, the Yangtze River. The result? A 5 million ton freight corridor that slashes costs, accelerates trade, and turns a once-forgotten region into a key economic hub. The numbers tell the story. Since the lift's completion, shipping costs from Guizhou have dropped by 67%. Industrial output has increased by 42%. Foreign investment has surged by 83%. Previously, uneconomical industries, from advanced manufacturing to agriculture, are suddenly viable. A province once known for subsistence farming now hosts technology parks and export zones. Villages that once clung to existence now thrive as service centers for the new shipping corridor. Thousands of jobs have been created, not just in shipping, but in maintenance, logistics, and supporting industries. Tourism itself has boomed, with the lift becoming a destination for both domestic and international visitors fascinated by this engineering wonder. But here's the bigger picture. This isn't just about regional development, it's about fortifying China's domestic supply chains. Imagine if international shipping lanes were suddenly disrupted. Ports close, sanctions tighten, global trade grinds to a halt. How does China keep its economy moving? That's where massive inland infrastructure like this becomes critical. The Gupitan ship lift is part of a broader network that includes the Three Gorges Dam, the south to north water transfer project, and thousands of kilometers of inland waterways. Together, they form an internal circulation system, one that can keep goods flowing even if external arteries are severed. This isn't merely speculation. China's dual circulation economic policy explicitly prioritizes developing resilient domestic supply chains that can function independently of global systems if necessary. Projects like the Gupitan ship lift are physical manifestations of this strategy. While the world obsesses over China's skyscrapers, bullet trains, and megacities, it's the hidden supply chains, the ones buried in the mountains and rivers, that might determine its future. These projects receive less international attention, but may ultimately prove more consequential. The ship lift also represents a powerful geoengineering approach to climate adaptation. As weather patterns become more extreme, water management becomes increasingly crucial. Systems like the Gupitan ship lift help regulate water flow, prevent flooding, and ensure continued navigability despite changing rainfall patterns. This ship lift isn't just a machine, it's an insurance policy, a chess move in a global economic game, a physical manifestation of China's long-term strategic thinking. So was this built for efficiency or to future-proof China against global uncertainty? The answer, increasingly, appears to be both. China's Gupitan ship lift isn't just an engineering marvel, it's a statement. A $7.7 billion vertical highway that bends mountains to its will, slashes trade routes, and reshapes entire regions. But it's also just one piece of a much larger puzzle. Similar projects are already under construction throughout China's western provinces. The technology developed for Gupitan is being refined, scaled, and expanded. Future lifts may be even taller, faster, and more efficient. Moreover, this expertise is becoming an export product itself. Chinese engineers who worked on Gupitan are now consulting on similar projects in Southeast Asia, Central Asia, and Africa as part of the Belt and Road Initiative. The knowledge gained from one impossible project fuels dozens more. If China can pull this off, what's next? Because while the world watches their skyscrapers rise and bullet trains blur, it's what's happening beneath the surface, the hidden infrastructure, that might change everything. And if this is just a piece of a larger plan, how far is China willing to go? $5.5 billion, 16,400 feet above sea level, 550 kilometers of strategic highway. Here's the blueprint for China's next power move in Asia. A massive highway is being carved through the Himalayas, creating a direct pipeline for Chinese influence straight to India's doorstep. What looks like infrastructure is actually a geopolitical weapon. While the world watches elsewhere, Beijing's newest alliance-building strategy unfolds in the world's highest mountains, and it could reshape the global power balance forever. The Trans-Himalayan Highway, also known as the China-Nepal Highway, stretches approximately 550 kilometers from Lhasa, the capital of Tibet, to Kathmandu, Nepal's capital city. But the true engineering challenge lies in the final 100 kilometers, a section that crosses the Himalayas through terrain previously considered impassable by modern roads. Let's put this in perspective. The highway crosses multiple passes above 5,000 meters. That's over 16,400 feet. At these elevations, atmospheric pressure drops to nearly half of what you experience at sea level. Workers need supplemental oxygen. Construction equipment performs at reduced capacity. Avalanches, landslides, and extreme temperature fluctuations are constant threats. The cost? Current estimates put it at $5.5 billion. But like many Chinese megaprojects, the final price tag will likely be much higher. Construction began in 2019, with sections already operational, and the entire highway is scheduled for completion in 2026. What makes this project different from other mountain roads is its classification as a true highway, designed for high-speed, high-volume transportation with multiple lanes, tunnels through the highest peaks, and dozens of major bridges spanning deep valleys. When completed, what once took a week of treacherous mountain driving will be reduced to approximately 10 hours. Building at the roof of the world brings unprecedented challenges. The Trans-Himalayan Highway passes through a region known for its geological instability. The Himalayan range isn't just tall, it's young and still growing, rising several millimeters each year as the Indian tectonic plate continues its collision with the Eurasian plate. This active geology means Chinese engineers face constant battles with unstable mountainsides, frequent earthquakes, and unpredictable weather patterns. In 2015, Nepal experienced a devastating 7.8 magnitude earthquake that killed nearly 9,000 people. Any infrastructure in this region must be built to withstand similar events. The engineering solutions are as ambitious as the project itself. To overcome the most challenging sections, China is employing tunnel boring machines specially modified for high-altitude operations. These massive machines, some as long as a football field, are cutting through solid mountain rock at elevations where the reduced oxygen makes conventional equipment struggle. Elevated roadways that float above unstable terrain. Rather than cutting into avalanche-prone slopes, many sections are being built on pillars, allowing snow and debris to pass underneath. A network of climate-controlled way stations. These facilities provide emergency services, oxygen supplies, and shelter from extreme weather conditions. Specialized concrete mixtures designed to withstand extreme temperature fluctuations. Regular concrete would crack and fail under the daily freeze-thaw cycles experienced at these elevations. One of the most impressive features is the Gairong Tunnel, a 10-kilometer passage being drilled directly through Mount Everest's neighboring peaks. When completed, it will be among the highest major tunnels in the world, with a maximum elevation of over 5,300 meters inside the mountain. The project employs over 2,000 workers, many of whom must undergo high-altitude conditioning before beginning their rotations. Living and working conditions are extreme, with temperatures ranging from minus 40 degrees Celsius in winter to 30 degrees Celsius in summer. To understand why China is investing billions in this highway, we need to look beyond engineering and focus on geopolitics. The Trans-Himalayan Highway represents something much more significant than a road. It's a strategic move in China's long game for regional dominance. For centuries, the Himalayas have served as a natural buffer between China and the Indian subcontinent. This massive mountain range has limited trade, cultural exchange, and, importantly, military movements between these ancient civilizations. The new highway effectively punches a hole through this buffer. For Nepal, the highway offers an economic lifeline. As a landlocked nation, Nepal has historically been dependent on India for access to the sea and international markets. Nearly 80% of Nepal's imports have traditionally come through India. The Trans-Himalayan Highway changes this equation dramatically, giving Nepal direct access to Chinese ports and reducing its economic dependence on India. This shift is already visible in Nepal's politics. Since construction began, Nepal has signed multiple trade and transit agreements with China, including deals that allow Nepal to use Chinese ports for third-country trade. This marks a significant pivot away from its traditional reliance on India. From India's perspective, the highway represents a serious strategic concern. India and China have a complicated relationship marked by a long-standing border dispute that erupted into armed conflict as recently as 2020 in the Galwan Valley. The Trans-Himalayan Highway potentially allows China to move military assets close to the Indian border much more rapidly than before. India has responded with its own infrastructure push, accelerating construction of border roads and strategic tunnels. But the pace of India's projects has lagged behind China's, creating what military analysts call an infrastructure gap that could have serious implications in any future conflict. But perhaps the most significant aspect of this project is its role in China's broader Belt and Road Initiative, BRI. Launched in 2013, the BRI aims to connect China with countries across Asia, Africa, and Europe through a network of roads, railways, ports, and other infrastructure projects. The Trans-Himalayan Highway represents a critical link in this network, opening new trade routes that bypass traditional sea lanes controlled by the United States and its allies. Beyond geopolitics, the Trans-Himalayan Highway promises to reshape economic realities across the region. Currently, trade between China and South Asia is constrained by geography. Goods must either travel by ship through the Malacca Strait and the Indian Ocean, a journey of weeks, or take limited land routes through Pakistan or Myanmar. The new highway could reduce transportation times between Lhasa and Kathmandu from days to hours. This efficiency gain translates directly into economic opportunity, potentially increasing China-Nepal trade from the current $1.5 billion annually to over $10 billion within a decade after completion. For China, the highway also serves domestic economic goals. Tibet, despite massive infrastructure investment, remains one of China's poorest regions. The highway connects Tibet more closely with markets to the south, potentially stimulating local industries and tourism. Chinese officials have specifically highlighted how the project will help alleviate poverty in Tibet's border regions. The economic ripple effects extend beyond the immediate region. Bangladesh, Bhutan, and northern India could all see increased Chinese trade and investment flowing through this new corridor. Chinese companies are already positioning themselves to build industrial parks and special economic zones near the highway's southern terminus. However, this economic opportunity comes with risks. Many economists warn that smaller economies like Nepal could face a debt trap scenario, where Chinese-financed infrastructure creates dependency and potential leverage for China. Similar concerns have been raised about other BRI projects in countries like Sri Lanka, where inability to repay loans resulted in the government leasing a strategic port to China for 99 years. Nepal's leaders insist they are aware of these risks and are navigating them carefully. But the economic gravity of a superpower next door is difficult to resist, especially when that superpower is building a highway directly to your capital. The Himalayan region is one of the most ecologically sensitive areas on the planet, often called the third pole because it contains the largest ice mass after the Arctic and Antarctic. Its glaciers feed major river systems that sustain nearly 1.5 billion people across Asia. Environmental experts have raised serious concerns about the Trans-Himalayan Highway's impact on this fragile ecosystem. Construction activities have already triggered landslides in several areas. The highway cuts through previously remote regions, bringing pollution, noise, and human activity to pristine environments. Of particular concern is the project's potential impact on water security. The Himalayas are the source of 10 major river systems, including the Ganges, Indus, Yangtze, and Yellow rivers. Disruption to natural water flows could have downstream consequences for billions of people who depend on these river systems for agriculture and drinking water. Climate change is already affecting the region, with Himalayan glaciers melting at accelerating rates. Some environmental scientists warn that large-scale infrastructure projects like the highway could exacerbate these effects, creating a feedback loop of environmental degradation. Chinese officials counter these concerns by pointing to environmental protection measures incorporated into the highway's design. These include wildlife crossings, reforestation efforts, and slope stabilization techniques designed to minimize erosion. They argue that improved access will actually help conservation efforts by making it easier to monitor and protect remote areas. However, independent environmental assessments have been limited, with restricted access to construction zones making it difficult to verify these claims. Environmental groups continue to push for greater transparency and more rigorous impact studies. As we look to the future, the Trans-Himalayan Highway raises profound questions about the changing dynamics of Asia. This single infrastructure project embodies larger trends reshaping the continent. China's rising influence, shifting alliances, the tension between economic development and environmental protection, and the evolving relationship between geography and power. For Nepal and other small states in the region, the highway presents both opportunity and challenge. Greater connectivity promises economic benefits, but also increases vulnerability to external pressures. Maintaining sovereignty and strategic autonomy while benefiting from Chinese investment will require skillful diplomacy. India faces perhaps the most complex strategic calculations. Does it attempt to counter China's infrastructure push with projects of its own? Does it accept a diminished role in Nepal and focus on other priorities? Or does it seek accommodation with China, finding ways to benefit from the new connectivity while protecting core interests? For China, the highway represents another step in its transformation from a regional power to a global one. By reshaping the physical landscape, China is also reshaping political realities. The ability to project economic and potentially military power across the Himalayas fundamentally alters strategic equations that have held for generations. The Trans-Himalayan Highway also offers a window into a future where infrastructure increasingly serves as a tool of statecraft. In a world where traditional forms of power projection face growing constraints, the ability to build connections, physical, economic, and political, becomes increasingly valuable. The machines continue their work in the thin Himalayan air, cutting through rock that has stood for millions of years. With each kilometer of pavement laid, the balance of power in Asia shifts slightly. What was once impossible becomes inevitable. The mountains that have separated civilizations for millennia are being bridged. But here's the question that keeps military planners and geopolitical analysts awake at night. If China can build a highway through the world's highest mountains in just a few years, what else might be possible? A train just broke the sound barrier of ground transportation. China's new maglev can hit 620 miles per hour. That's faster than a Boeing 737 at takeoff. While the rest of the world argues about electric cars, China built a train that makes airplanes look slow. But here's what nobody's talking about. This technology might not even be Chinese. And the real story behind this machine could change how every country thinks about the future of travel. Most people think trains are slow. Heavy metal boxes rolling on metal tracks. But China just shattered that idea completely. Their new maglev prototype hit 387 miles per hour in testing. The final version is designed for 620 miles per hour in a vacuum tube. To put this in perspective, a commercial airplane cruises at around 550 miles per hour. This train would be faster than flying. The technology works through magnetic levitation. Instead of wheels touching tracks, powerful magnets lift the entire train above the guideway. No friction means no speed limit from contact. The train floats in a controlled magnetic field, pushed forward by electromagnetic forces. It's like a bullet shot through a magnetic cannon, except the bullet is a passenger train. But speed is just the beginning of this story. Here's where things get complicated. Maglev technology wasn't invented in China. It was developed in Germany in the 1960s. German engineers created the first working maglev systems. They built test tracks and prototype trains decades before China entered the game. The Transrapid system in Germany could reach 268 miles per hour back in the 1980s. German companies spent billions developing this technology. They had working systems while most countries were still using diesel trains from the 1950s. But Germany made a critical mistake. They never scaled up production. Political debates about cost and environmental concerns slowed development. The technology remained trapped in research facilities and short test tracks. So how did China end up with the world's fastest maglev? The answer involves technology transfer deals, joint ventures, and what some engineers call strategic acquisition of foreign expertise. In the early 2000s, China needed to upgrade its transportation system fast. They invited German companies to build maglev systems in China. The deal seemed simple. Germans would provide the technology, Chinese companies would handle construction. Both sides would benefit. Shanghai got the first commercial maglev line in 2004. Built by German company Transrapid, it connected the airport to the city centre. The 19-mile track took just 8 minutes to complete at top speed. But technology transfer agreements have fine print. Chinese engineers worked alongside German experts. They learned the systems inside and out. They studied every component, every design principle, every manufacturing process. Within a few years, Chinese companies understood maglev technology as well as the Germans who invented it. Then China did what China does best. They took that knowledge and improved it. China's obsession with speed isn't about bragging rights, it's about economic survival. The country has 1.4 billion people spread across a massive territory. Moving people and goods efficiently isn't just convenient, it's essential for keeping the economy running. Traditional transportation creates bottlenecks. Highways get clogged, airports reach capacity limits. Even China's impressive high-speed rail network, currently the world's largest, has constraints. Trains still touch tracks, which creates wear, noise, and speed limits. China's current high-speed rail system covers over 25,000 miles. That's more than the rest of the world combined. But even these trains max out at around 217 miles per hour in regular service. For a country trying to connect cities separated by thousands of miles, that's still too slow. The economic math is simple. Time equals money. Every hour saved in transportation multiplies across millions of passengers. A businessman who can travel from Beijing to Guangzhou in 3 hours instead of 8 can close deals faster and generate more economic activity. Consider the economics. A maglev line between Beijing and Shanghai could move passengers in under 2 hours. The same trip takes 4.5 hours on China's fastest conventional high-speed train. Cut travel time in half, and you essentially double the economic productivity of both cities. The secret to reaching 620 miles per hour isn't just magnetic levitation, it's the vacuum tube system. Most maglev trains still fight air resistance. At high speeds, pushing through air becomes the biggest obstacle to going faster. Think about it this way. A car needs more fuel to go from 60 to 80 miles per hour than from 40 to 60 miles per hour. Air resistance increases exponentially with speed. At 300 miles per hour, air resistance becomes a brick wall. At 600 miles per hour, it's like trying to push through concrete. China's solution is elegant and ambitious. Put the entire maglev system inside a tube with reduced air pressure. Less air means less resistance. Less resistance means higher speeds with the same energy input. It's the same principle that makes space travel possible. Remove the atmosphere, and you can go as fast as your propulsion system allows. The engineering challenges are enormous. These tubes need to be perfectly sealed across hundreds of miles. They require massive pumping systems to maintain low air pressure. Temperature changes cause expansion and contraction that could crack the tubes or misalign the tracks. The vacuum tube maglev represents a completely new category of transportation. It's faster than driving, more efficient than flying for medium distances, and more comfortable than either option. Passengers experience smooth acceleration without the turbulence of air travel or the vibrations of road transport. Other countries are watching China's maglev development with a mixture of admiration and concern. If successful, this technology could give China a massive economic advantage. Fast, efficient transportation networks drive economic growth. Countries with better infrastructure attract more investment, create more jobs, and generate more wealth. The United States is taking notice. American companies are exploring their own vacuum tube transportation systems. Elon Musk's Hyperloop concept shares similarities with China's approach, though it uses different technology for levitation and propulsion. Several startups are working on competing systems, but most remain in early testing phases. The difference is scale and commitment. While American companies test small prototype systems, China is building full-scale infrastructure. They're not just proving the technology works, they're proving it can work at national scale. Europe is in a difficult position. German companies developed the original maglev technology, but they never built it at the scale China is attempting. European transportation infrastructure is advanced but fragmented across many countries with different standards and regulations. Japan has its own maglev program. Their system can reach 375 miles per hour and will connect Tokyo to Osaka by 2027. Japanese engineering is world-class, and their safety standards are exceptional. But even Japan's impressive technology looks slow compared to China's 620 miles per hour target. China understands this dynamic perfectly. They're not just building trains, they're building economic dominance. Building vacuum tube maglev systems requires enormous upfront investment. Initial cost estimates for China's network run into hundreds of billions of dollars. The Shanghai maglev line cost approximately $1.2 billion for just 19 miles of track. That's roughly $60 million per mile. But China's government takes a different view. They see infrastructure spending as long-term economic investment. A maglev network that lasts 50 years and transforms transportation across the country justifies massive initial costs. The economic benefits compound over decades. Traditional cost-benefit analysis doesn't capture the full value of revolutionary infrastructure. When the interstate highway system was built in America, critics called it wasteful spending. Decades later, economists estimate it generated economic benefits worth trillions of dollars. China also benefits from scale economics. They're building multiple maglev lines simultaneously, spreading development costs across many projects. Manufacturing components in large quantities reduces per-unit costs. The government financing model makes ambitious projects possible that would be impossible under pure market economics. Despite the impressive progress, vacuum tube maglev technology faces significant challenges. Maintaining low air pressure across hundreds of miles of tube requires constant energy input. The vacuum pumps alone consume enormous amounts of electricity. Engineers estimate that maintaining partial vacuum could require the output of multiple power plants. Safety systems become more complex when trains travel at 620 miles per hour in sealed tubes. At 620 miles per hour, a train travels more than 900 feet per second. Traditional braking systems can't handle these speeds safely. Emergency stops from maximum speed could take several miles and generate dangerous heat levels. Weather impacts create additional complications. Temperature changes cause tube expansion and contraction. A temperature swing of 100 degrees could cause miles of tube to expand by several feet. That's enough to misalign the magnetic levitation system. Earthquake zones need special engineering to prevent track misalignment. Even small movements could cause the levitation system to fail. China's engineers are addressing these challenges through extensive testing and redundant safety systems. But every solution adds complexity and cost to the overall system. China's 620 miles per hour maglev represents more than transportation technology. It's a statement about technological leadership and economic ambition. The country that masters ultra-high-speed ground transportation could gain decisive advantages in the 21st century economy. Other nations are responding with their own ambitious projects. The competition is driving innovation across multiple technologies: magnetic levitation, vacuum systems, power electronics, and advanced materials. This technological race benefits everyone through faster development and better solutions. India announced plans for its own Hyperloop system connecting major cities. Saudi Arabia included Hyperloop connections in its futuristic city projects. Russia announced research into vacuum tube transportation systems connecting Moscow to distant regions. Even developing nations don't want to be left behind in this race. The implications extend beyond transportation. Vacuum tube technology has applications in cargo transport and industrial processes. Magnetic levitation could revolutionize manufacturing and energy storage. The innovations developed for 620-mile-per-hour trains will likely find uses in completely different industries. China understands these broader implications. They're not just building infrastructure, they're building the foundation for future dominance across multiple sectors. The maglev project is part of a larger strategy to lead the world in advanced technologies. But there's something else happening that most people haven't noticed yet. Something that could make even a 620-mile-per-hour train look like old technology. And it's already being tested in a secret facility just outside Beijing. A massive white bubble, taller than a 15-story building, suddenly appears over a construction site in China. Workers inside are building the future, while the outside world hears nothing. No dust clouds choking nearby residents, no thunderous machinery waking families at dawn. This is not science fiction. This is China's latest weapon in the war against construction pollution, and it might just change how the world builds forever. China builds more in a single year than most countries construct in a decade. Since 2012, building construction funding has increased by 30%. Subway systems are expanding 5 times faster than any other nation. By 2020, China had built 8,000 kilometers of new subway lines alone. But this construction boom comes with a dark side. In major Chinese cities, construction noise accounts for over 25% of all noise complaints. Beijing residents face average noise levels exceeding 70 decibels. The health impact is severe. Studies show construction noise causes cardiovascular disease, sleep disorders, and cognitive problems. Children and elderly populations suffer the most. Construction dust pollution creates another crisis. Heavy metals like zinc, chromium, and lead contaminate the air around building sites. These particles spread for miles, affecting air quality in residential areas. Research shows that construction dust contains dangerous levels of PM 2.5 particles, the same pollution that causes respiratory disease. Enter Jinan, the capital of Shandong province. City officials decided to tackle this problem with something the world had never seen. In July 2025, they unveiled a 50-meter-tall inflatable dome covering 20,000 square meters. This structure is not just big, it is revolutionary. The dome uses no internal supports, no columns, no beams. Instead, it relies on constant air pressure to maintain its shape. Made from PVDF-coated polyester, the material is fire-resistant and can withstand extreme weather. 38 steel cables anchor it to the ground, creating a stable platform for construction work. Inside, advanced ventilation systems manage air quality. Transparent sections allow natural light to enter, reducing the need for artificial lighting. Temperature and pressure sensors regulate air circulation. At exhaust points, water misting systems capture airborne particles, dramatically reducing dust emissions compared to open-air construction sites. Creating a structure this large requires precise engineering. The dome maintains its shape through continuous air pressure systems. Multiple air pumps work around the clock, ensuring stability. The membrane material must be strong enough to resist wind loads while remaining flexible enough to inflate. Weather resistance was crucial. The dome must function during rain, snow, and extreme temperatures. Engineers designed the material to expand and contract without losing structural integrity. This flexibility allows the dome to withstand typhoons and harsh winter conditions common in northern China. Installation takes just days, not weeks. The modular design means the dome can be quickly assembled, inflated, and secured. When construction finishes, the entire structure can be dismantled and moved to another site. This reusability makes it cost-effective compared to traditional noise barriers. Local residents noticed immediate changes. Air quality measurements show significant improvement in dust levels around the construction site. Workers inside the dome report better working conditions. The controlled environment protects them from extreme weather, allowing construction to continue during rain and snow. The interior remains cooler in summer and warmer in winter, improving productivity and safety. The dome creates a unique construction environment. Without wind interference, precise work becomes easier. Material handling improves because dust does not blow around the site. Equipment operates more efficiently in the controlled atmosphere. China's construction pollution problem mirrors challenges worldwide. India's major cities face similar issues with construction dust and noise. Mumbai, Delhi, and Bangalore all struggle with building-related air pollution. European cities like London and Paris have implemented strict construction noise regulations, but enforcement remains difficult. The United States spends billions annually on construction-related health costs. The Occupational Safety and Health Administration has established exposure limits for construction dust, but monitoring remains challenging. Urban density makes the problem worse as more people live closer to construction sites. This innovation addresses more than environmental concerns. Construction delays caused by noise complaints cost developers millions. Legal disputes over environmental violations create additional expenses. The dome system reduces these risks by containing pollution at the source. Project timelines improve because weather delays decrease. Rain and snow no longer stop construction work. This efficiency translates to faster project completion and reduced costs. Developers can work longer hours without disturbing nearby residents. The reusable nature of the dome creates economic advantages. Traditional noise barriers and dust control systems are often single-use. The inflatable dome can move from project to project, spreading costs across multiple construction sites. Beijing has already begun testing similar technology in the Lizhe financial district. City officials offer incentives for builders adopting gas membrane systems. Shanghai and other major cities are watching the Jinan experiment closely. International interest is growing. Indian cities are studying the technology as a solution to their construction pollution problems. European engineering firms are analyzing the dome's design for potential adaptation. The technology could spread globally if proven effective. The dome represents broader trends in construction technology. Smart sensors monitor air quality in real time. Automated systems adjust ventilation based on activity levels. This integration of technology and construction points toward future building methods. Not everyone embraces this innovation. Some experts worry about heat buildup inside the dome during summer months. Professor Liu Wei, an environmental engineer, warns of potential heat stress risks for workers. The enclosed space could become dangerously hot without proper ventilation. Cost remains a significant factor. The dome system requires substantial initial investment. Smaller construction projects may not justify the expense. Questions remain about long-term maintenance costs and replacement schedules. Critics argue the dome only shifts pollution rather than eliminating it. While dust and noise stay contained, the underlying environmental impact of construction continues. The dome does not address material waste or energy consumption during building. This innovation reflects China's approach to urban development challenges. Rather than accepting construction pollution as inevitable, Chinese engineers created a technological solution. This mindset drives innovation in other areas of infrastructure development. The dome connects to China's broader environmental goals. The country aims for carbon neutrality by 2060. Reducing construction pollution supports these objectives while maintaining rapid urbanization. The technology demonstrates how environmental protection and economic development can align. Smart city initiatives benefit from this innovation. Cleaner construction processes support the development of sustainable urban environments. The dome technology could become standard equipment in future smart city projects. The Jinan dome might represent the beginning of a construction revolution. Imagine every major building project enclosed in a smart, responsive dome. Construction sites could become clean, quiet, and efficient workspaces. Urban residents would no longer suffer from building-related pollution. Advanced versions could integrate even more technology. Solar panels on the dome surface could power construction equipment. Rainwater collection systems could provide water for dust suppression. The dome could become a self-sufficient construction environment. International adoption would create a global market for this technology. Chinese manufacturers could export dome systems worldwide. This technology transfer would generate economic benefits while improving global construction practices. Other countries are developing alternative solutions. Japanese companies are creating robot-operated construction systems that reduce human exposure to dust and noise. European firms are designing modular construction methods that minimize on-site work. The United States is investing in prefabricated construction technologies. These systems reduce on-site construction time and associated pollution. However, none match the comprehensive approach of the Chinese dome system. The race for construction innovation is accelerating. Countries that develop effective solutions will gain economic advantages in the global construction market. The Jinan dome positions China as a leader in this emerging field. The success or failure of this experiment will influence urban development worldwide. If the dome proves effective and economical, it could become standard practice in major cities. Construction pollution could become a problem of the past. However, if the system fails or proves too expensive, it could set back efforts to address construction pollution. The global construction industry will watch closely to see if this innovation delivers on its promises. The stakes extend beyond environmental concerns. This technology could determine which countries lead the next generation of urban development. The dome represents more than pollution control. It symbolizes the future of how humans build cities. Now, if you think building with air is futuristic, wait until you see what Europe and Africa are about to pull off. This $7 billion tunnel doesn't just break barriers, it rewrites history. And it's real. Click to see how they're making it happen.